The Large Magellanic Cloud, a nearby galaxy sculpted by the power of stars. But what secrets hide within this galactic companion of the Milky Way today? We'll travel across its glowing clusters and vast nebulae to uncover its story. If you enjoy this journey, please like, subscribe and share, and in the comments tell us which part of the universe you dream of exploring next. Thank you for watching. Now, let's begin. The Large Magellanic Cloud sits in the southern sky as a modest, irregular patch of light, but its outermost extent stretches far beyond what is seen with the naked eye. The faint halo surrounding this companion galaxy is revealed through careful surveys that look for ancient stars spread thinly across a wide region of sky. These stars are not bright or dramatic. They are quiet variables known as RR Lyrae pulsating in steady rhythms, with periods measured in hours. Because the relationship between their period and intrinsic brightness is well calibrated, astronomers can determine their distances with confidence. When the brightness of many RR Lyrae stars is measured across the sky, a pattern emerges that traces the faint edge of the Large Magellanic Cloud. Their distribution extends well outside the main bar and disk, demonstrating that the galaxy is larger and more diffuse than first impressions suggest. Globular clusters also mark this extended boundary. Only a handful are linked with the Large Magellanic Cloud, but those present lie at considerable distances from the central regions. They contain stars that are over 10 billion years old and deficient in heavy elements, pointing to formation at the dawn of the galaxy's history. Their survival in the outskirts indicates that the gravitational field of the Large Magellanic Cloud reaches far outward. By charting their positions, astronomers gain another anchor for the size of the stellar halo. Together with the RR Lyrae variables, the clusters confirm that the system extends tens of thousands of light-years far beyond what is visible in ordinary optical images. Surface brightness measurements provide a quantitative way to define the halo. Starting from the bright bar, star counts fall smoothly as radius increases. They do not vanish abruptly. Instead, the density decreases until it blends with the background of the Milky Way's own halo stars. To separate one population from the other, astronomers rely on color magnitude diagrams that distinguish stars by age and metallicity. With these techniques, the faint envelope of the Large Magellanic Cloud becomes visible as a statistical signal. Careful subtraction of foreground contamination reveals a low-density halo that would otherwise be impossible to detect. The halo is not uniform. Certain directions show overdensities that resemble streams or arcs. These may be relics of past tidal interactions with the Milky Way or with the small Magellanic Cloud. To confirm their membership, astronomers turn to measurements of proper motion, the tiny shifts in stellar positions over years. Observations from the Gaia mission are precise enough to distinguish stars belonging to the Large Magellanic Cloud from those in the foreground. When mapped this way, the outskirts reveal coherent structures that extend away from the main body, giving a record of gravitational disturbance over cosmic time. Spectroscopic studies add a chemical dimension. The halo stars are generally metal-poor, meaning they contain little more than hydrogen and helium. This is consistent with formation in the earliest epochs of star formation. Some stars, however, show slightly higher metallicities, implying that the halo is not a single population but a mixture. Perhaps it includes stars stripped from small satellites that merged with the Large Magellanic Cloud long ago. The presence of such stars suggests that even a companion galaxy of modest size experienced a history of accretion and merging. The geometry of the halo is complex. Distance indicators show that the Large Magellanic Cloud is tilted relative to our line of sight. As a result, one side of the halo appears closer, the other farther. This tilt means the outer contours on the sky are elongated, not circular. To model this structure, astronomers combine distance measurements with spatial mapping to reconstruct the three-dimensional form. The outcome is an extended tilted halo that stretches differently along different axes, reflecting both intrinsic shape and perspective from Earth. The faint outskirts also inform mass estimates. The radial extent of stars that remain bound requires a substantial dark matter halo. Without dark matter, the outer clusters and RR Lyrae stars would have been stripped away by tidal forces. Models that fit the observed distribution indicate that the Large Magellanic Cloud may be more massive than once believed, possibly containing a dark halo that approaches 1/10 the mass of the Milky Way. Such mass alters predictions of orbital evolution and affects how strongly the galaxy interacts with its neighbours. Gas adds another component. Neutral hydrogen extends into the outskirts, overlapping with the stellar halo but stretching still farther. Radio observations at 21 centimeters. Map this diffuse gas, revealing filaments and patches that show velocity gradients. The gaseous boundary does not align with the stellar edge, illustrating how gas is more easily affected by external forces such as ram pressure and tidal stripping. This discrepancy between gas and stars is important for understanding the overall environment of the Large Magellanic Cloud. Detecting the halo requires patience and precision. Observers use wide-field cameras that cover degrees of sky and integrate light for long periods to capture faint stars. Data reduction involves careful removal of foreground stars and background galaxies, leaving behind the sparse but coherent population that belongs to the Large Magellanic Cloud. The resulting maps provide the frame of reference for all subsequent exploration. They mark the outermost locations where the galaxy maintains coherence, and they supply the boundary conditions for dynamical models. Within these outskirts lie subtle signs of assembly. Groups of stars with shared motion and chemical properties hint at disrupted systems. Streams arcing across the halo point to encounters that stretched and redistributed stars. Each detection adds to the narrative of how the Large Magellanic Cloud formed and evolved in a busy cosmic neighborhood. These features show that the outer halo is not an empty shell, but a record of events preserved in low-density stellar populations. At the very limit of detectability, astronomers log positions, brightnesses, and motions of tracers, and feed them into dynamical models. The spread of stellar velocities sets limits on the gravitational potential. Overlapping survey tiles build a mosaic that defines where the galaxy ends and where the background dominates. These painstaking efforts ensure that the map of the halo is accurate enough to serve as a foundation for deeper studies further inward. At the outer limit of the Large Magellanic Cloud, the view shifts from a faint halo to elongated arrangements of stars that extend away from the main body, as pale, continuous ridges that sit low against the background. These ridges are stellar streams, thin on the sky and easiest to follow when the gaze traces their coherence from one field to the next. A first stream appears as a gentle arc that bends around the outskirts, with a radius too large for a single frame. Its stars are subdued in colour and brightness, white or soft yellow points that collect into a ridge that rises only slightly above the field, yet remains steady in direction. The arc proceeds for a long distance, fading and strengthening with changes in background density, but the line persists and can be recovered after each thin stretch by returning to the last clear segment and stepping outward again. A second stream runs more directly away from the central regions, a slender filament that keeps a nearly constant orientation as it crosses the background. The spacing between stars along this filament is larger, and individual sources are easy to pick out, yet the alignment holds through the gaps and remains visible across adjacent fields. Within both streams, knots of higher density appear. These are modest enhancements rather than massive clusters, but they stand out because the surrounding light is diffuse. In each knot, the number of stars per small area rises above the average, along the ridge forming a short bright segment before the density falls back. The alternation of knots and quieter spans gives a gentle rhythm that helps to hold the path in view as the streams cross regions of uneven background. Crossings occur where one stream passes over another, and at such places the combined density increases just enough to register as a small rise in brightness. One path follows a broad arc, while the other proceeds more linearly, producing an X-shaped overlay when both are traced, and each stream continues with its own width and orientation beyond the overlap. The widths of the streams vary with position. Some segments remain narrow over long distances only a few star separations across, while other segments broaden gradually into shallow fans where the alignment is visible but more diffuse. In a fan, the central crest is present, yet stars spread laterally so that the edges blur and no firm boundary is seen. Narrow filaments, in contrast, retain a tighter concentration and a clearer spine that allows the ridge to be followed even where the surroundings become busy. Depth is subtle but present. Portions of a stream can appear slightly nearer or slightly farther than neighbouring segments, not because the line shifts on the sky, but because the distribution of stars along it occupies a range of distances. The streams are volumes rather than drawings, and the mixture of nearer and farther stars gives the ridges a mild sense of layering. In several areas, the streams taper into zones where star counts are only slightly above the field, and continuity becomes the guide. Even when the contrast is low, the line maintains direction and curvature over many arc minutes, and if the alignment holds across successive fields, the feature remains identifiable as a stream. The point at which it can no longer be traced is not a sharp edge, but a gradual transition where the count matches the background and the orientation is lost. Local conditions affect the visibility. A light veil of dust reduces apparent brightness and creates short gaps that close when the veil thins. In fields where the background of Milky Way stars grows denser, the streams appear fainter by comparison, even if the intrinsic density does not change. Bright foreground stars, small clusters, and field galaxies can mask short spans. The outermost parts of the streams show small lateral offsets, and gentle wiggles smooth departures from a best-fit line, measurable only over large angular scales. In some segments, the ridge bends slightly toward the galaxy, and in others it bows outward. The deviations are small compared with the length of the streams and do not interrupt continuity. Near several ridges, compact clusters sit on, or just beside the spine, and provide convenient waypoints that mark positions along the flow. In addition to arcs and filaments, there are broad fans in which the density gradient is shallow, and the alignment is expressed by an elongated maximum rather than a narrow crest. Fans can be traced by sampling perpendicular slices and finding the center line that maintains the highest counts over successive positions, and following that center line shows that the structure persists even when the edges merge with the background. Some fans narrow again at larger radii, collecting back into a filament before thinning below detectability. Across the outskirts, the background itself gains and loses density with position, and streams remain identifiable when their alignment crosses such gradients without turning with them. Taken together, several ridges in the outer region differ in length, width, curvature, and surface brightness. They extend away from the brighter disk into areas where the material is sparse, and they thread across the outer field, sometimes crossing one another and sometimes running alone for long stretches. Where mapping reaches current depth, the lines thin until they cannot be separated from the surrounding stars, Beyond the faint arcs of stars, the outer regions of the Large Magellanic Cloud open into a domain where light no longer comes from stars alone. Here the presence of the galaxy is marked by neutral hydrogen gas, a material invisible to the human eye but mapped through careful listening to radio waves. When wide fields are examined at the 21 centimeter line, the galaxy appears wrapped in a vast irregular cloak. It is not smooth or even. Instead, it spreads outward in fingers and wisps, each one a filament extending well beyond the bright disk that most images reveal. The cloak is patchy with thick knots beside regions that are thin, giving the impression of a landscape with valleys and ridges drawn in gas. As one drifts inward from the streams of stars, the first impression of this gas is its sheer scale. The stellar envelope fades after a certain distance, but the hydrogen continues covering an area on the sky many times larger than the disk. On one side, the gas broadens outward into a diffuse sheet, while on another side it narrows into thinner strands. The outlines are uneven, showing how the galaxy does not end at a clean edge, but merges into space with a halo that changes character depending on direction. The emission strength of this hydrogen reflects how much gas lies along the line of sight. Near the core of the galaxy, where material is dense, the signal is strong. Moving outward, it declines gradually, yet even at the farthest radii, faint emission remains detectable, carrying with it information about motion and position. These faint traces show that the Large Magellanic Cloud has a presence that far exceeds what can be seen in optical light. Looking northward, the hydrogen does not simply fade into the background. It streams away in long tails that stretch far beyond the limits of the stellar disk. These tails connect to the much larger Magellanic Stream, a structure that arcs across a significant fraction of the southern sky. The gas there is continuous, beginning in the outer envelope of the Large Magellanic Cloud and extending outward as a great trail. To the south, the extensions are shorter, forming wisps that curve back toward the disk before dissolving into space. The asymmetry is striking. One side shows long filaments, the other only compact clouds. In the opposite direction, ahead of the galaxy's motion, lies another feature. Clouds appear as if pushed forward, forming the structure known as the leading arm. These clouds are faint and broken, but when followed across successive fields, they form a coherent lane. Between the large and small Magellanic Clouds, the hydrogen forms a dense bridge. It is broad and bright in the radio maps, filling the space between the two companions with gas. Within this bridge, stars are also present, scattered associations that likely formed from the same material. The bridge appears less like a separate feature and more like a natural continuation of the envelopes of both galaxies meeting in the middle. Within the halo, denser clumps of gas break the pattern of diffuse filaments. Some clumps are compact, spanning only a few hundred light-years, while others are long complexes thousands of light-years in length. Their brightness stands above the surrounding material marking regions where gas has pooled. In some of these clumps, star formation has occurred, producing small groups of young stars that shine faintly amid the envelope. Elsewhere, the clumps remain purely gaseous, drifting silently without stellar companions. The gas is not uniform in state. Much of it is neutral, but ultraviolet light from the galaxy's hot stars and shocks from stellar explosions have ionized parts of it. These ionized regions are detected as diffuse glows in ultraviolet surveys, revealing layers above and below the disk where radiation has reached. Dust grains are also mixed into the envelope. Though sparse, they are traced by the way they absorb and scatter background starlight, causing subtle dimming and reddening across certain fields. The halo is therefore a mixture of neutral hydrogen, ionized hydrogen, and dust, each component adding a layer to the outer structure. The velocity field of the gas adds further dimension. Near the disk, the hydrogen rotates with the galaxy. Farther out, the motion becomes distorted. Some filaments drift ahead, others lag behind, and gradients appear along their lengths. One filament shows a steady increase in velocity outward, while another slows and becomes nearly stationary relative to the galaxy. These variations show that the gas is not bound in the same way as the inner disk. Some of it remains loosely attached, while other portions are already moving outward into larger flows. Viewed across the sky, the hydrogen halo forms a vast uneven shape. It is thicker in the north, narrower in the south, and marked by filaments that reach out like arms. The patchwork nature of the mission gives the impression of a dynamic, unsettled structure. Each filament can be followed across many degrees, some tapering gradually, till they vanish, others widening into fans before dissolving. The continuity of these features is clear even when brightness falls near the limit of detection. Moving inward, the density of gas increases, the signal strengthens, and the distribution becomes smoother, though still punctuated by clumps. The transition is gradual. There is no sudden boundary between the faintest filaments and the main body. Instead, the gas thickens steadily, building toward the brighter regions that define the inner disk. The outer envelope thus forms a broad region of transition, a place where gas extends far into space, but remains linked to the galaxy. In the faintest reaches, the emission merges with the noise of the background. Filaments that were once clear lines fade into irregular patches and then into nothing detectable. The last traces appear as weak signals only marginally above the surrounding field. Beyond that, the halo cannot be separated from the background sky. The transition is soft, not abrupt, as though the galaxy slowly dissolves into space without leaving a sharp edge. Closer toward the disk, the extended hydrogen envelope begins to blend into larger tidal features that mark the interaction of the Large Magellanic Cloud with both the Small Magellanic Cloud and the Milky Way. These features do not exist as isolated structures, but appear connected like streams of gas that continue the halo outward into space. The most striking is the Magellanic Stream, a ribbon of hydrogen that extends across more than 100 degrees of the sky. It trails behind the two galaxies arching across the southern hemisphere in radio maps. In places the stream is narrow and filamentary, in others it spreads into multiple lanes that weave around one another. Its brightness varies with dense knots interspersed by stretches of fainter emission, but the continuity of the flow is unmistakable. The stream carries a clear velocity pattern, gradually changing as it winds away from its origin. Observers trace it across vast distances, confirming that it originates from the Magellanic Clouds and now stretches deep into the halo of the Milky Way. In the opposite direction lies the leading arm, another filament of gas but less extensive and more broken. It appears ahead of the motion of the system, as if gas has been pushed forward or stripped by external forces. The leading arm is divided into several segments that span tens of degrees, each one fragmented into clouds and filaments. These fragments vary in density and shape, but together they form a coherent structure pointing away from the Large Magellanic Cloud. Their velocities differ from those of the main disk, confirming that they are displaced components of the system's gaseous halo. Though less continuous than the trailing stream, the leading arm is still a significant extension of the galaxy into its environment. Between the Large and Small Magellanic Clouds lies the Magellanic Bridge, a band of gas that links the two companions directly. The bridge is denser than the more diffuse features, appearing as a clear lane of hydrogen emission that fills the space between the galaxies. Within it, astronomers have identified young stellar associations showing that star formation is possible, even in this tenuous environment. The bridge is not uniform. It contains clumps and filaments, some bright and compact, others elongated. The gas connects smoothly into the envelopes of both galaxies, so that the bridge does not begin or end abruptly, but merges into their outer layers. The tidal features are not limited to one direction or one scale. Smaller filaments branch from the mainstream, some curving back toward the Milky Way, others bending away. These side filaments are faint, barely above detection limits, but they add complexity to the structure. Clumps of gas are scattered along them, sometimes appearing isolated, other times forming short chains. The sky maps show that the outskirts of the Large Magellanic Cloud are not just a halo but a network of gaseous extensions that stretch in multiple directions. The velocities of these features tell part of the story. Along the Magellanic Stream, velocities shift gradually, showing how the gas moves relative to the Milky Way. Each segment carries a consistent velocity pattern, and together they form a gradient that can be followed for tens of thousands of light years. The leading arm has its own velocity structure distinct from the main disk, but coherent across its fragments. The bridge shares velocities with both galaxies, sitting between them in both space and motion. These patterns demonstrate that the gas is dynamically linked to the galaxies, while also extending into the broader environment. The appearance of the tidal features depends on the wavelength of observation. In radio maps at 21 centimeters, they appear as diffuse ribbons of emission. In ultraviolet absorption studies, they appear as shadows against the light of background quasars, showing their composition and ionization state. Some portions are mostly neutral, while others are partially ionized with gas stripped into different phases. Dust is also present, though in small amounts. Its signature is detected in reddening of background sources, indicating that solid grains have been carried along with the gas. The spatial extent of these features is enormous. The Magellanic Stream alone covers more sky than the full moon thousands of times over. The leading arm and bridge add further breadth surrounding the galaxies with structures that are far larger than their visible disks. To the observer, the effect is that the Large Magellanic Cloud does not appear as a compact island of stars, but as the center of a wide field of gaseous extensions. Each extension stretches for tens of degrees, making the system appear entangled with its environment. The morphology is complex but continuous. Filaments split and merge, brightness rises and falls, but there are no sharp boundaries. Instead, the gas thins gradually until it cannot be separated from the background. Clumps linger at the edges, some detached, others connected by thin strands. Each portion adds to the sense that the galaxy is surrounded by material in motion, extended far beyond the limits of the stellar disk. As one follows these features across the sky, the impression is of a galaxy whose outer layers are open and connected rather than closed. The tidal structures reach outward, linking the Large Magellanic Cloud to its companion and to the Milky Way. They form paths of gas that stretch across space, fragile yet coherent, visible only with the right instruments but spanning extraordinary distances. Their presence ensures that even far from the bright bar and disk, the galaxy continues to project structures outward, making its environment part of its observable form. From the gaseous bridges and tidal streams, the view drifts gradually inward to the outer parts of the disk of the Large Magellanic Cloud. Here the system takes on a more recognizable form, not simply a halo of faint stars and gas, but a flattened structure with rotation and a defined orientation. This disk is inclined relative to our line of sight so that one edge appears closer while the other lies farther away. The tilt can be measured by comparing the apparent brightness of standard candles such as red clump stars and pulsating variables across different regions of the galaxy. Stars on the nearer side appear slightly brighter, while those on the far side appear slightly fainter, and the difference reveals the geometry of the disk. The line of nodes, the axis along which the tilt is defined, runs diagonally across the face of the galaxy, giving it the appearance of a sheet turned at an angle rather than lying flat. As the gaze follows, the disk rotation becomes evident. Stars and gas in one half move toward us, while those on the opposite half move away, the result of the galaxy spinning about its center. This rotation is not only seen in radial velocities of stars, but also in the motion of hydrogen gas, whose 21 centimeter line can be tracked across the entire disk. The pattern shows a clear gradient with velocities rising to a maximum at intermediate radii, before flattening at larger distances. This behavior is a classic sign of a rotating disk, one that is supported not only by the visible stars and gas, but also by an extended halo of unseen mass. The inclination and rotation together give the disk a three-dimensional presence. When mapped carefully, the shape resembles a shallow bowl with one rim lifted higher than the other. The stars fill this bowl unevenly, more crowded toward the central bar, sparser toward the edges. Yet the motion is coherent. Stars in the outskirts still follow the general rotation even as tidal interactions pull them into slight distortions. The disk as a whole appears lopsided, with one side more extended than the other, a sign that the system has not fully settled into a symmetric form. Within the disk, metallicity varies with radius. Stars near the center are generally richer in heavy elements, while those in the outskirts are poorer. This gradient arises from the way successive generations of stars enrich the gas from which new stars form. In the inner regions, where star formation has been more sustained, enrichment is stronger. Farther out, where star formation has been less continuous, the chemical abundance remains lower. The result is a subtle but measurable gradient that records the history of star formation across the disk. The outer disk is not smooth. Spiral-like patterns appear faint but discernible in maps of young stars and gas. These arms are not as pronounced as the grand spirals of larger galaxies, yet they trace regions where gas has compressed and formed associations of hot, luminous stars. They curve gently outward from the bar, extending into the disk with irregular shapes. Some are more complete, while others are broken into segments. The presence of these features suggests that density waves or tidal forces have imposed order on the gas, guiding the formation of new stars into patterns that resemble arms. As the exploration moves inward, large associations of stars come into view. These associations are scattered across the disk, forming loose groups that outline the spiral-like structures. Each association contains dozens or hundreds of young stars, bright and blue, standing out against the older, redder background population. The associations are embedded in gas, often accompanied by clouds of hydrogen that remain from the star-forming process. They are spread unevenly, with some regions showing many associations and others appearing quiet. This unevenness reflects the patchy nature of star formation, where some parts of the disk are active while others lie dormant. The disk also contains older populations. Red giants populate the background, filling the field with steady light. Their distribution is smoother than that of the young associations, providing a foundation against which the younger features stand out. The contrast between the two populations illustrates the layered history of the disk. Old stars provide the skeleton, while young stars highlight the current activity. The balance between them shifts with radius, with the outer disk dominated by older populations, and the inner disk showing more mixed layers. The motion of gas within the disk adds further structure. Radio maps show streams and arcs that follow the rotation, but also reveal perturbations. Some arcs bend slightly away from circular motion, showing that the disk is not perfectly stable. These deviations are signs of gravitational interactions that have disturbed the system. Despite the irregularities, the overall rotation remains clear, giving the disk a sense of coherence even amid its asymmetry. Dust is present throughout the disk, concentrated along certain lanes. These lanes appear as dark bands against the background of stars absorbing light and creating subtle shadows. In infrared maps, the dust glows faintly, remitting the light it has absorbed. The lanes follow the spiral-like features, indicating that they are part of the same structures that shape star formation. Dust grains are small but numerous, and they play a central role in cooling gas and enabling it to collapse into new stars. Their distribution therefore highlights the regions where future associations may appear. Toward the edge of the disk, the brightness falls off gradually. The stellar density decreases and the lanes of dust become thinner. Gas is still present, but its emission is weaker and more irregular. The rotation curve flattens, showing that material continues to move coherently, even at large radii. Beyond this, the disk merges into the streams and halo already described, linking the structured inner regions with the diffuse outer layers. The transition is gradual without a sharp edge, blending one component into another. At this distance inward, the Large Magellanic Cloud presents itself as a tilted rotating disk, irregular in shape but coherent in motion. Its asymmetry, metallicity, gradient, and spiral-like features all mark it as a system shaped by both internal processes and external influences. The view at this stage is not of an isolated disk, but of a structure whose orientation, motion, and composition can be traced in detail, forming the framework for the regions still closer to the centre. Deeper inside the disk of the Large Magellanic Cloud, the view becomes more complex as the geometry of the system is no longer defined solely by inclination and rotation, but also by asymmetry. The most prominent feature here is the bar, a thick band of stars that crosses the central region. Unlike the symmetric bar seen in many spiral galaxies, this bar is not centered within the disk. It lies offset, displaced slightly from the middle, creating the impression that the galaxy is unbalanced. This off-center placement has been recognized in many surveys where the bar appears shifted toward one side, while the outer disk extends farther on the opposite side. The effect is not subtle. It is one of the defining characteristics of the Large Magellanic Cloud. The bar itself is dense with stars. It glows with the light of intermediate-age populations many billions of years old, mixed with younger stars formed in recent epochs. Its surface brightness is higher than that of the surrounding disk, giving it a visual prominence even against the crowded field of the galaxy. The stars within the bar are not arranged smoothly. Pockets of higher density occur along its length, with clusters and associations interwoven into the general population. Dust lanes run through it as well, absorbing light and marking regions where gas is still present. These dark lanes, though thin, give the bar texture and variation. Rotation within the bar differs from that of the outer disk. Velocities measured across the region show that stars move in elongated orbits, aligned with the bar rather than in simple circles. This kinematic pattern gives the bar its elongated form and maintains its structure against dissolution. The bar acts as a channel redistributing stars and gas within the galaxy. Its offset position indicates that the dynamics of the Large Magellanic Cloud are unusual, influenced by tidal interactions and by internal resonances that keep the bar stable despite its displacement. The asymmetry of the bar affects the appearance of the disk. On one side of the bar, spiral-like arms extend outward, populated by star-forming regions and associations. On the other side, the disk is less developed with fewer arms and a different distribution of gas. This imbalance produces the lopsided look that is visible even in wide-field photographs. The galaxy does not present a symmetric face, but rather one that is stretched more in some directions and compressed in others. The bar stands as the central anchor of this irregular system, yet even it is not positioned at the true geometric center. Metallicity measurements across the bar reveal gradients that differ from those of the disk. Stars within the bar are on average more enriched than those in the outskirts, but the pattern is not uniform. Some regions contain populations of lower metallicity, suggesting that the bar has captured stars from older epochs. Others are enriched by recent star formation marked by young clusters and supergiants. The mix of ages and abundances gives the bar a layered history representing multiple episodes of formation and growth. Gas in the vicinity of the bar shows disturbed motions. Clouds of neutral hydrogen bend around the bar, their velocities shifted by the gravitational potential. Ionized regions are present along its length, produced by young stars that continue to form there. The interaction between gas and stars within the bar is ongoing, with inflows of material feeding star formation and feedback from massive stars shaping the local environment. Superbubbles and shells carved by stellar winds and supernovae are seen in several locations, providing evidence of recent energetic activity. The stellar populations within the bar include both old and young members. Red giants dominate the background, filling the structure with steady light. Interspersed among them are younger, bluer stars that have formed in the last few 100 million years. Clusters of varying age dot the bar, some compact and rich, others loose and extended. The diversity of populations highlights the continuous activity within the bar, where star formation has not ceased but has continued in cycles. The bar also influences the disk around it. Gravitational resonances create patterns in the gas distribution, guiding material into certain orbits and leaving gaps in others. These resonances may be responsible for some of the spiral-like features seen in the outer disk. They also concentrate gas toward the inner regions, enhancing the rate of star formation within and near the bar. The result is a system where the central structure not only holds stars but also regulates the flow of gas, acting as a driver of galactic evolution. The off-center placement of the bar remains one of the puzzles of the Large Magellanic Cloud. Most barred galaxies have their bars aligned with the geometric center, yet here the displacement is clear. The cause may lie in the interactions with the Small Magellanic Cloud and the Milky Way, which have perturbed the system repeatedly. Another possibility is that internal dynamics alone, such as asymmetries in the dark matter halo, have shifted the bar. Whatever the origin, the effect is that the bar defines the visible center of the galaxy, while leaving the true mass center elsewhere. Moving along the bar, the density of stars is high, but it tapers toward the ends. At each end, the bar appears to connect with spiral features, though not in a symmetric fashion. One end leads to prominent star-forming complexes, while the other connects more loosely to diffuse arms. The transitions are gradual, not sharp, with the bar blending into the disk through intermediate features. Dust and gas accompany these transitions, marking them as sites of active change. The overall impression at this stage is of a galaxy whose inner disk is dominated by a bar that is bright, dense, and displaced. The bar governs local dynamics, organizes stellar populations, and interacts with gas to produce new generations of stars. It stands out not only as the visual heart of the system, but also as the structural element that sets the Large Magellanic Cloud apart from many other galaxies of similar size. Advancing further inward, the view begins to shift from the broad sweep of the bar and its off-center placement to the material that fills the surrounding disk and the complex gradients of composition that trace the chemical history of the Large Magellanic Cloud. As one moves across the face of the galaxy, the stars reveal different levels of enrichment. Near the outer edges, where the disk thins into faint associations, the stars are older and their light carries the spectral fingerprints of lower metallicity. They formed long ago from gas that had not yet been heavily enriched by earlier generations of stars. Their light is steady and subdued, giving the outskirts a quiet background of redder tones. Closer to the interior, the populations change. Stars are younger on average, and their spectra reveal higher abundances of elements heavier than helium. This gradient is not abrupt but gradual, as though one is moving along a slope where each step inward adds a little more enrichment to the population. The metallicity gradient is not uniform across the disk. Some sectors show patches of higher abundance than their radius would predict, while others show lower. These irregularities arise because star formation is not evenly distributed. Large associations form in certain regions, and their massive stars enrich the surrounding gas when they end their lives. In neighbouring regions that remain quiet, the gas stays less enriched. The result is a patchwork of chemistry superimposed on the overall gradient. When plotted in detail, the metallicity map resembles a landscape of hills and valleys, each one marking a place where a star formation has left its imprint. The presence of young metal-rich stars is clearest along the spiral-like arms. These arms, although not as sharply defined as in grand spiral galaxies, serve as sites where gas has been compressed, triggering new star formation. Within them, bright blue stars shine, and the gas around them is already enriched by earlier cycles. The arms act as pathways of higher metallicity threading through the disk. Between them, older populations dominate and the metallicity is lower. This contrast gives the disk a textured composition both in age and in chemical content. Clusters within the disk illustrate the history in more detail. Ancient globular clusters scattered across the system contain stars that are extremely metal-poor, their compositions frozen from the earliest epochs. Intermediate age clusters only a few billion years old show higher metallicities, marking a period when the galaxy was more active and more enriched. Still younger clusters less than a billion years old carry the signatures of even greater enrichment. By studying clusters of different ages and comparing their chemical content, astronomers can trace the evolution of the galaxy's metallicity across time. The disk is therefore a layered archive, with each cluster preserving a chapter of its past. Gas within the disk reflects the same gradients. Spectra of hydrogen clouds and emission from H2 regions show higher metallicities nearer the centre and lower metallicities farther out. This pattern is consistent with the idea that gas cycles inward and outward, carrying the products of stellar nuclear synthesis with it. Supernovae release elements into the surrounding medium, and winds from massive stars disperse them further. Over time, the inner regions where star formation is most active accumulate more enrichment. The outer regions, less active, remain closer to their primordial state. The effect of metallicity is visible not only in chemical analysis, but also in the colours and temperatures of stars. Metal-rich stars often appear slightly redder at a given mass and age, while metal-poor stars appear bluer. This subtle difference adds to the gradient seen across the disk. Fields dominated by metal-poor stars have a different overall colour balance than those dominated by metal-rich ones. Observers can see the shift even without spectroscopy by comparing photometric maps across the face of the galaxy. The distribution of metallicity also interacts with the structure of the disk. The offset bar lies within a region of relatively higher enrichment, reflecting the repeated star formation that has occurred there. Spiral-like arms connect to this bar and extend outward, carrying gradients of their own. The edges of the arms are not chemically uniform. Some segments are enriched by recent episodes, while others remain older and less enriched. This unevenness shows how local processes shape the global gradient. Supergiants within the disk provide another perspective. These luminous stars, short-lived and massive, form in the enriched gas of the inner regions. Their spectra reveal abundances that reflect the most recent chemical state of the gas. By comparing their composition to that of older stars in the same area, one can measure how quickly the metallicity has risen. The presence of supergiants concentrated along certain arms indicates that the rise has not been uniform but strongest, where new stars continue to form most rapidly. Intermediate-age stars add yet another layer. These stars, several billion years old, fill the disk with a widespread population. Their metallicities are higher than those of the halo, but lower than those of the younger stars. Their presence ensures that the disk does not belong exclusively to either the ancient or the very young, but holds a broad mix. They smooth the gradient into a continuum, bridging the gap between extremes. The mapping of metallicity relies on many techniques, from spectroscopy of individual stars to analysis of star clusters and emission from gas clouds. Each method adds detail to the picture. Together they confirm that the Large Magellanic Cloud is chemically diverse, with gradients that reveal both its radial structure and its irregularities. The richness of the inner disk contrasts with the simplicity of the outskirts, while the offset bar adds its own layer of complexity. As the view lingers on the disk, the gradient is not seen as a simple line, but as a surface rippled with variations. The stars and gas reflect histories of formation enrichment and dispersal, each part of the disk telling a slightly different version of the same story. The irregularities are as much a part of the structure as the overall trend, ensuring that the galaxy cannot be described by a single gradient alone, but must be understood as a mosaic. At the outer edges of this region, the enriched stars thin out and the metallicity slopes downward again. The disk connects gradually back into the halo, and the streams beyond where old metal poor stars dominate once more. The transition marks the limit of the disk's chemical influence, blending the inner richness into the outer simplicity without a sharp divide. Moving still farther inward, the disk of the Large Magellanic Cloud shifts from gradients of composition toward regions where new stars are actively forming. The outskirts of the disk show only faint associations, loose gatherings of young stars scattered against a background of older populations. These associations are widely spaced, each containing only a modest number of bright members. Their blue light contrasts with the reddish tones of the surrounding field, marking them as recent products of gas that has only just condensed. Between these associations lie broad stretches of quiet sky, where little star formation is visible. The distribution is patchy, not continuous, reflecting the uneven density of gas in the outer disk. Following the arc of the disk inward, the faint associations gradually give way to more organized features that resemble spiral arms. These arms are not grand or symmetric, but appear as partial arcs where gas has gathered and compressed. Within them, stars are more numerous, and young clusters appear in greater concentration. Their arrangement outlines a pattern of motion within the disk, as though material has been guided into lanes where conditions are favourable for star formation. Dust is visible along these arms as thin, dark filaments, absorbing background starlight and tracing the sites where gas is densest. The arms curve gently, extending away from the central bar, each one marking a corridor of recent activity. Inside these arms, the gas is not uniform but clumpy. Large clouds of neutral hydrogen and molecular material appear as reservoirs for future star formation. Some clouds already contain H2 regions, glowing bubbles of ionized gas where massive young stars have recently ignited. The contrast between the dark clouds and the bright regions illustrates the transition from potential to active star formation. Observers following these arms can trace a sequence: clouds gather, stars form, and radiation then illuminates the surroundings. The arms thus appear as laboratories of stellar birth. Closer to the centre, the spiral-like arms host larger and more luminous complexes. Some regions span hundreds of light-years, filled with clusters, associations, and ionized gas. The Tarantula Nebula is the most prominent of these, but it is not alone. Several other H2 regions shine brightly, each one marking the presence of massive stars whose radiation and winds sculpt the gas. These complexes appear irregular in shape, filled with arcs, filaments, and cavities. Their internal structure is the product of feedback as young stars inject energy into their environment and push material outward. The Tarantula Nebula dominates the scene with its extraordinary size and brightness. It is the largest star-forming region in the local group, a vast cloud of gas and dust illuminated by thousands of young stars. At its core lies a cluster so rich that it contains many of the most massive stars known, some dozens of times the mass of the Sun. Their radiation ionizes the gas, producing a luminous glow that extends for hundreds of light years. The nebula's filaments twist and branch, creating a web-like structure that justifies its name. Cavities within the cloud mark places where supernovae and winds have carved out space, leaving behind shells of swept-up material. The tarantula is visible even at great distances, its brightness outshining entire galaxies beyond the local group. Beyond the tarantula, other luminous H2 regions appear across the disk. Each one is smaller but still significant. They occur along the arms and near the ends of the bar where gas is compressed and star formation is strongest. Some are isolated, glowing bubbles surrounded by dark clouds. Others are connected into chains forming sequences of regions along a single arm. Their distribution shows that star formation is not confined to one location, but is spread across the disk, concentrated where conditions favor collapse. The stellar populations within these regions are dominated by massive short-lived stars. They shine brightly in blue and ultraviolet light, producing the ionization that makes the regions glow. Around them are clusters of less massive stars still young, but destined to live much longer. The mix of populations shows that star formation produces a full range of stars, not only the massive ones that dominate the light. Embedded within the clouds are still younger stars hidden from view by dust but detectable in infrared surveys. These embedded populations indicate that star formation is ongoing, not just a past event. Dust within the star-forming regions plays a major role in shaping their appearance. Dense lanes obscure portions of the nebulae, creating dark patches against the glowing background. In infrared, these lanes glow faintly, revealing the presence of heated dust grains. The dust marks the places where gas is densest and where future stars are likely to form. Its distribution is uneven, forming knots and filaments rather than smooth sheets. As feedback from young stars clears, some regions dust is pushed into shells that surround the bright cores. The interaction between star formation and feedback is evident in the superbubbles that fill parts of the disk. These superbubbles are cavities tens or hundreds of light years across, created by the combined winds and explosions of massive stars. Their walls are lined with glowing gas while their interiors are more tenuous. The shapes are often irregular with breakouts, where the hot gas has escaped into the surrounding medium. These structures demonstrate that star formation is not a quiet process, but one that actively reshapes its environment, carving cavities and driving flows that extend far beyond the initial site of birth. As one moves along the arms toward the central bar, the concentration of star-forming regions increases. The arms become brighter and more structured, filled with clusters, associations, and nebulae. The bar itself connects with these features, guiding material inward and concentrating gas near its ends. Star formation is especially active at these junctions where gas is compressed by the gravitational potential of the bar. The result is a sequence of luminous regions that trace the connections between bar and arms. At the inner edge of the disk, the star-forming activity begins to thin, giving way to regions dominated by older populations once again. The bright nebulae fade, replaced by steadier light from red giants and intermediate-age stars. The transition is gradual, with patches of young activity interspersed among older fields. This mix highlights the layered nature of the disk where star formation has occurred repeatedly across time and space. The overall effect is of a galaxy whose inner disk is alive with ongoing creation, punctuated by regions of intense activity and surrounded by quieter zones that hold the results of earlier cycles. Deeper into the Large Magellanic Cloud, the stellar populations reveal the full range of ages from the most ancient clusters to the most luminous young stars. The contrast between these populations is stark, and their coexistence within one system shows how the galaxy has carried its history forward while continuing to produce new generations. At the oldest end are globular clusters, dense spheres of stars that formed more than 10 billion years ago. These clusters are scattered through the outer halo as well as within the disk, and they provide a fossil record of the earlier stages of the galaxy. Their stars are faint and metal-poor, glowing with the subdued light of great age. Each cluster contains hundreds of thousands of stars bound tightly together, resistant to dispersal. Their survival until the present shows that they formed early and endured through the many tidal encounters that have shaped the system. Between the globular clusters and the current star-forming regions lie populations of intermediate age. These stars formed a few billion years ago during episodes when the galaxy was more active than it is today. They are found both in clusters and as field stars spread throughout the disk. Their metallicities are higher than those of the ancient populations, but lower than those of the youngest. This intermediate age population is especially prominent in the bar where the density of stars is high and the evidence of sustained star formation over long periods is clear. The light from these stars gives the bar its glow, filling it with steady brightness that contrasts with the patchy nebulae of the arms. Superimposed on these older layers are young populations formed within the last few 100 million years. Cepheid variables are among the most important of these. Their pulsations make them reliable standard candles, and their presence throughout the disk provides a map of distances and structure. The Cepheids shine brightly their regular changes in brightness, marking them as indicators of the most recent star-forming cycles. Alongside them are red supergiants, massive stars near the end of their lives. They are rare but extremely luminous, visible from far away despite their small numbers. Their light is deep red, and they appear as striking beacons against the background of fainter stars. Young clusters add another layer. Some are compact, containing thousands of stars, while others are loose associations spread across wide areas. The compact clusters are dominated by massive blue stars that illuminate the surrounding gas. The loose associations contain stars of various masses, many still embedded in dust. These clusters show that star formation occurs in both concentrated bursts and extended gatherings. Their distribution across the disk is uneven, with concentrations along arms and near the bar. The presence of both compact clusters and loose associations demonstrates the diversity of environments where stars are born. Massive stars play a crucial role in shaping the galaxy. Their ultraviolet radiation ionizes surrounding gas, creating H2 regions that glow across the disk. Their winds carve bubbles and shells, disrupting nearby clouds. When they explode as supernovae, they enrich the interstellar medium with heavy elements, adding to the chemical gradient described earlier. These processes mean that the presence of a few massive stars can influence large areas of the galaxy. The feedback they provide regulates further star formation, sometimes triggering it in nearby clouds, sometimes dispersing gas and halting it. The oldest populations are not restricted to clusters. Field stars throughout the disk include ancient red giants and variable stars such as Aurora Lyrae, which serve as tracers of the earliest epochs. Their presence within the disk shows that the galaxy has mixed its populations over time, spreading old stars into regions where younger ones dominate. The mix produces a layered field where stars of many ages coexist, each carrying information about the epoch of its birth. The interplay between these populations creates a complex age structure. In some regions, young stars dominate the light, while in others, older stars provide the background. Clusters of different ages are often found close together, showing that star formation has been recurrent in the same locations. The age structure is patchy rather than uniform, shaped by the movement of gas and the influence of feedback. This patchiness is visible even in broad surveys which reveal that the Large Magellanic Cloud is not a system of simple radial age zones, but one of overlapping generations. Variable stars offer insight into both age and structure. Cepheids trace young populations while RR Lyrae trace the old. By mapping their distributions, observers can see how the galaxy contains both ancient and recent layers. The Cepheids outline the disk and arms following the paths of current star formation. The RR Lyrae extend into the halo, marking the remnants of the earliest formation. Together they provide a three-dimensional map of the system, each group highlighting a different era. Clusters remain important anchors of this history. The ancient globular clusters, the intermediate age populous clusters, and the very young associations all coexist within the Large Magellanic Cloud. Their properties record the chemical and dynamical history of the galaxy, each one a capsule of a different time. Their spatial distribution is uneven, with some concentrated in the bar and arms others scattered more widely. This unevenness shows how the galaxy has built itself in segments, forming and dispersing clusters across billions of years. In the inner disk, supergiants stand out as especially luminous markers. They dominate their local environments both visually and physically. Around them, smaller stars cluster, benefiting from the enrichment and feedback that the massive stars provide. These supergiants live short lives, and their presence means that star formation in their regions must have been very recent. They therefore serve as temporal markers, indicating which associations are youngest. The contrast between these bright giants and the dimmer older stars around them emphasizes the continuous renewal occurring within the galaxy. The coexistence of all these populations makes the Large Magellanic Cloud a system rich in contrasts. Ancient stars lie alongside young clusters. Metal-poor globular clusters sit near regions glowing with enriched gas. Long-lived red giants share the disk with luminous supergiants on the verge of collapse. The mixture creates a dynamic field of light, where every region holds evidence of multiple epochs. The galaxy is therefore not a uniform population, but a layered collection of stars of many ages, each one contributing to the present view. At the edges of this region, the young populations thin, and the view transitions once more into fields dominated by older stars. Yet even here, isolated associations remind the observer that star formation continues scattered across the disk in pockets of activity. The balance between old and young is never entirely settled, ensuring that the Large Magellanic Cloud displays the full spectrum of stellar ages across its breadth. Moving farther inward, attention shifts from the mix of stellar populations to the medium that lies between them. The interstellar matter of the Large Magellanic Cloud is not uniform, but exists in many phases, from dense molecular clouds to diffuse ionized gas, and each phase interacts with the others through energy motion and pressure. This medium forms the setting in which stars are born, evolve, and eventually return material through winds and explosions. Seen across the disk, the gas and dust do not form a smooth backdrop but appear as clouds, filament shells, and cavities. The complexity is the result of continuous processes that stir and reshape the medium. Dense molecular clouds are the most obvious birthplaces of stars. They appear as dark patches against the brighter fields of starlight, absorbing and scattering visible light. In infrared views, however, they glow faintly warmed by the stars forming inside them. These clouds range in size from small knots only a few parsecs across to giants spanning dozens of parsecs. Within them, cold gas and dust gather into clumps where gravity overcomes internal pressure, leading to the collapse that forms new stars. The densest cores remain hidden, visible only in long wavelength observations, while their surroundings reveal filaments and threads of dust. Surrounding the molecular clouds are H2 regions glowing volumes of ionized hydrogen. These are created by the radiation of young massive stars that strip electrons from surrounding atoms. The resulting gas shines in characteristic emission lines, giving these regions their luminous appearance. In the Large Magellanic Cloud, H2 regions vary in size from small bubbles around individual clusters to enormous complexes like the Tarantula Nebula. Their shapes are irregular, sculpted by the distribution of gas and by the forces of stellar winds. Bright edges mark the boundaries where radiation meets neutral gas, and filaments trace the paths where ionization fronts advance. In addition to discrete H2 regions, the disk contains diffuse ionized gas spread more broadly. This component fills much of the space between stars, giving the interstellar medium a pervasive glow. It is maintained by the combined radiation of many stars and by shocks from supernovae. Though less dense than the localized regions, it contributes significantly to the overall structure. Its presence is confirmed by faint emission that extends beyond the boundaries of bright nebulae, showing that ionization is not limited to specific clouds, but reaches across the disk. Neutral hydrogen remains the most widespread phase. It fills vast areas of the disk mapped through its radio emission. In some places it collects into arcs and shells, in others into broad sheets. Its distribution reflects the influence of stellar feedback. Where massive stars have exploded, cavities appear in the neutral gas bordered by shells of higher density. These shells are often hundreds of light-years across, enclosing regions that have been cleared by winds and supernovae. The neutral hydrogen thus records the history of energetic events, each cavity a marker of a past explosion or cluster of massive stars. Superbubbles stand out among these features. They are created when multiple massive stars in a cluster release winds and explode in sequence, combining their energy into a single large cavity. The result is a hollow region filled with hot, tenuous gas surrounded by a shell of swept-up material. Superbubbles in the Large Magellanic Cloud can reach diameters of several hundred light-years. Some remain closed, while others have ruptured, venting hot gas into the surrounding medium. These ruptures create channels through which energy escapes, linking the interiors of superbubbles with the larger halo. Hot gas is also present that are invisible in optical light. Observations in X-rays reveal extended regions of million-degree plasma, produced by the combined action of supernovae and stellar winds. This hot phase fills the interiors of superbubbles and leaks into the surrounding medium. It provides pressure that shapes the distribution of cooler gas, compressing it in some regions and dispersing it in others. Though tenuous, the hot phase has large effects because of its energy content. Its presence demonstrates that the interstellar medium is a dynamic balance of cold clouds, warm gas, and hot plasma. Dust grains are scattered throughout all these phases. Though small, they absorb and scatter light, altering the appearance of the galaxy. In optical images, they create dark lanes and patches. In infrared, they glow faintly, irradiating the energy they have absorbed. Dust is concentrated in molecular clouds, where it helps shield gas from radiation and enables it to cool. It is also carried into shells and bubbles, where it outlines the structures created by feedback. The distribution of dust provides a complementary map of the interstellar medium, one that highlights where gas is densest and where new stars are most likely to form. The cycle of matter in the Large Magellanic Cloud can be traced in this medium. Gas collects into molecular clouds, collapses into stars, and is then dispersed again by stellar feedback. Each phase feeds into the next, ensuring that the interstellar medium is constantly renewed. The mixture of clouds, ionized regions, neutral hydrogen superbubbles, and dust is not static, but evolving on timescales of millions of years. The galaxy appears not as a fixed arrangement, but as a system in motion with material continually shifting between phases. Across the disk, the scale of these structures is impressive. Some clouds span only a few parsecs, while some shells extend across hundreds. Superbubbles link regions separated by vast distances, while diffuse ionized gas permeates the whole disk. The interplay of scales means that the interstellar medium cannot be understood from a single viewpoint. It requires tracing features from the smallest knots to the largest cavities, each one a part of the same complex whole. As the gaze lingers on the interstellar medium, the field is filled with details. Filaments twist, cavities expand, and dust lanes weave through the light of countless stars. Bright nebulae highlight the regions where feedback is strongest, while quiet clouds mark places where new stars may soon emerge. The balance between light and dark, between emission and absorption, shows the constant interplay of creation and disruption. The Large Magellanic Cloud at this level is revealed as a living environment, its appearance shaped not only by stars but by the material that surrounds them. Closer to the center of the Large Magellanic Cloud, the bar and inner disk merge into regions where the density of stars is high, and the interplay between stellar birth and stellar death is especially visible. Here the evidence of feedback is stronger than in the outskirts. Shells and cavities fill the field, some only tens of light years across, others spanning hundreds. Each one is the product of energy injected into the medium by massive stars, either through winds or through the violent explosions that mark the end of their lives. The structures are layered with younger shells overlapping older ones, and with cavities that open into the larger medium. The result is a complex terrain where the shapes of gas and dust are determined not by calm rotation, but by repeated bursts of energy. The shells vary in form. Some are nearly circular, enclosing volumes of hot, thin gas. Others are irregular, stretched in one direction, where the surrounding medium is less dense. Bright rims of ionized gas trace the edges, marking where radiation and shock waves encounter neutral material. In some shells, the rims are broken, indicating that the pressure inside has burst through weak spots and vented into the surroundings. These ruptures create channels that link the interior of the shell with the wider interstellar medium. Through such channels, hot gas escapes, carrying energy and enriching material into regions far beyond the original site of star formation. Superbubbles dominate several areas of the inner disk. These are formed when clusters of massive stars act together their winds, and supernovae combining to excavate enormous cavities. Within them, the gas reaches temperatures of millions of degrees, glowing in X-rays though invisible to the eye. The shells of superbubbles are thick with swept-up material, often fragmented into arcs and filaments. Some superbubbles remain enclosed, while others have burst outward, their interiors connected to the halo through long chimneys of hot gas. The scale of these structures is vast, extending across hundreds of light years and influencing the dynamics of entire regions of the galaxy. Star-forming regions are embedded within this environment, showing how creation and destruction proceed side by side. Dense molecular clouds lie adjacent to shells, their surfaces compressed by expanding gas. Along these surfaces, new clusters emerge triggered by the pressure of earlier generations. In this way, star formation is propagated through feedback, one cycle seeding the next. The Tarantula Nebula is the most extreme example, where massive clusters continue to form within a region already shaped by powerful winds and explosions. But throughout the inner disk, smaller examples of the same process are visible, linking the history of starbirth and feedback in a continuous chain. The stellar populations in the central regions include not only young stars but also the remnants of past generations. Supernova remnants are scattered across the field, each one a record of a star that ended in an explosion. These remnants appear as expanding shells of gas rich in heavy elements that were created in the final stages of the star's life. Some are compact and bright, still fresh from the explosion, while others are larger and fainter, their energy dissipated into the surrounding medium. Together they enrich the galaxy with elements that will be incorporated into new stars and planets. Pulsars and compact remnants also reside here, though invisible without specialized instruments. These objects, the collapsed cores of massive stars, are small but dense, contributing little to the light of the galaxy, but marking the ultimate endpoint of stellar evolution. Their presence, though subtle, adds another layer to the complexity of the central regions. They are reminders that alongside the brilliance of star formation lies the inevitability of stellar death. Dust continues to play a major role shaping the appearance of the inner disk. Dense lanes thread through the bar, creating dark features against the light of millions of stars. In some places, dust outlines the edges of bubbles swept into filaments by expanding gas. In others, it lies in sheets blocking background light entirely. Infrared observations reveal these dust structures glowing faintly warmed by starlight. They are integral to the cycle, providing the cooling that allows gas to collapse into new stars even as feedback attempts to disperse it. The density of stars in the inner regions is striking. Red giants fill the background, their steady light forming the fabric of the bar. Superimposed on them are younger populations, clusters, and bright supergiants. The mixture creates a layered view, where every line of sight intersects stars of different ages and types. Variability is common, with pulsating stars changing brightness over days or weeks, adding a subtle rhythm to the field. These variables serve as tools for measuring distances and structure, but here they also contribute to the richness of the view. The kinematics of the central regions differ from those of the outer disk. The rotation is less regular, distorted by the presence of the bar and by interactions with nearby galaxies. Stars move in elongated orbits, and gas flows are channeled along certain directions. The velocity field is patchy, reflecting both the gravitational potential and the disturbances imposed by feedback. In some places, inflows of gas converge toward the bar, while in others, outflows from bubbles push material outward. The interplay creates a dynamic environment, one where equilibrium is continually disrupted and re-established. At smaller scales, the view is filled with detail. Filaments of ionized gas wind between clusters. Arcs mark the edges of cavities. Compact clusters shine with bright blue stars, while diffuse associations spread across larger areas. Supernova remnants glow faintly, their expanding shells overlapping with newer features. The landscape is crowded and restless, shaped by countless events occurring over millions of years. Yet amid the complexity patterns emerge shells nested within shells, bubbles adjacent to new clusters, and arcs that trace the flow of gas across the disk. As the exploration of the inner disk continues, the density of structures increases. Superbubbles connect, remnants overlap, and clusters appear in greater numbers. The cycle of starbirth and death is compressed into smaller regions, giving the center of the galaxy a character distinct from the outskirts. It is here within the crowded bar and its surroundings that the processes shaping the Large Magellanic Cloud are most clearly visible, not as isolated features, but as a continuous interplay of matter and energy. Closer to the heart of the Large Magellanic Cloud, the bar and surrounding regions display a density of stars so high that the background itself glows. The light of countless old giants fills the field, forming a fabric through which younger populations are scattered. Here the central density is not just a visual impression, but a measurable increase in stellar numbers, with the bar acting as a reservoir of stars from many epochs. The region is neither smooth nor featureless. Instead, it is marked by the consequences of feedback. Cavities, arcs, and superbubbles are more common here than in the outer disk, and each one testifies to the combined energy of massive stars and their supernovae. The complexity of the structures grows as one moves inward with layers of gas and dust woven together in a crowded environment. Massive clusters occupy prominent places along the bar. Some are so rich that they rival small galaxies in brightness, their combined light outshining surrounding fields. They are surrounded by halos of stars that extend outward into the disk, linking them to the broader population. Within these clusters, massive blue stars dominate each pouring radiation and winds into its surroundings. The effect is visible as glowing regions of ionized gas sculpted into arcs and filaments. Around these luminous zones, dust is pushed aside, creating clearings that contrast with darker lanes nearby. Supernova remnants are especially abundant in the central regions. Each remnant is an expanding sphere or shell of material moving outward at thousands of kilometers per second. Their sizes vary, with the youngest remnants still compact and bright, while older ones have expanded into diffuse arcs that fade into the background. Together they create a layered view of stellar death with remnants from many generations overlapping. The enrichment from these explosions is spread widely, ensuring that the gas in the central regions is heavily laced with elements forged in stars. This enrichment is visible in the high metallicities of younger populations, which formed from gas that has been processed repeatedly. Gas flows within the central regions are complex. Some streams funnel inward along the bar, carrying material toward the densest parts. Others are pushed outward by feedback, escaping through ruptures in shells and cavities. The result is a circulation of gas with inflows and outflows occurring simultaneously. The inflows feed new generations of stars while the outflows distribute energy and enrichment. Observations show arcs of hydrogen bending around cavities, dust lanes curving along the bar, and filaments stretching away from clusters. These structures are not static, but constantly reshaped by the balance of gravity, radiation, and pressure. The bar itself acts as a regulator of these flows. Its elongated potential channels stars and gas into orbits aligned with its axis, maintaining its structure, while distorting the rotation of the inner disk. Along its length, concentrations of young stars indicate where gas has collected and collapsed. These concentrations are not symmetric but occur in clumps, some near the ends of the bar, others along its sides. The asymmetry reflects the irregular nature of gas inflow and the influence of past interactions with the small Magellanic Cloud. The result is a bar that is not a uniform band but a textured structure filled with localized regions of activity. Variable stars populate the bar in large numbers. Cepheids trace the younger populations, their regular pulsations marking them as reliable beacons. RR Lyrae variables trace the oldest populations, providing evidence that the central regions contain both extremes of age. The coexistence of these variables demonstrates that the bar has been a site of star formation across the entire history of the galaxy, from its earliest epochs to the present. Their distribution reveals the depth of the bar, showing that it extends through the disk rather than lying as a flat feature. Dust lanes remain prominent, weaving through the light of the bar. Some lanes are narrow, absorbing light from small regions. Others are broader, spanning hundreds of light years and cutting across the bar like rivers of shadow. Infrared maps show these lanes glowing faintly heated by surrounding stars. The dust marks the locations where gas is densest and where future star formation may occur. It also shapes the appearance of the bar, breaking its light into patches and segments, rather than allowing a smooth glow. Star clusters of intermediate age are also common in the central regions. These clusters, formed several billion years ago, provide a bridge between the ancient globulars and the youngest associations. Their stars are enriched, but not as heavily as the youngest, showing that they were born when the galaxy was already chemically evolved, but not yet at its current level. They are stable and compact, holding their stars together in dense groups that have survived the turbulent environment of the bar. Their survival indicates that the bar, despite its activity, has been a long-lived structure capable of hosting populations across many epochs. The interstellar medium here is layered with structures created by feedback. Some cavities overlap, producing irregular shapes that defy simple description. Arcs bend into one another, filaments cross at angles, and dust sheets cut across shells. Each feature records a different event, whether a single supernova, a cluster wind, or the combined action of many stars. Together they create a crowded field where the history of energy release is written in overlapping lines. The density of such features increases toward the center, making the environment progressively more complex. As one moves deeper, the crowding of stars reaches a level where the background becomes continuous. Individual stars can still be distinguished, but the overall impression is of a solid field of light. Against this field, clusters, variables, and nebulae stand out as brighter or darker patches. The balance between light and shadow enrichment and depletion, young and old, gives the central regions of the Large Magellanic Cloud their distinctive character. The view is no longer of isolated structures, but of an environment where every part is connected, where feedback from one generation feeds into the formation of the next, and where the density of stars and gas creates a setting of constant change. At the very core of the Large Magellanic Cloud, the density of stars reaches its highest levels, filling every line of sight with overlapping populations. The bar narrows here into a crowded hub, where old and young stars blend, and where the influence of feedback continues to shape the surrounding medium. The central regions are marked not by one single structure, but by a layered combination of clusters, cavities and gas flows that overlap and interact. The density is such that the background appears as a continuous glow, only broken by the occasional dust lane or bright cluster. This glow is the combined light of countless red giants, each shining steadily with the energy of long lifetimes. They provide the fabric of the core against which younger and brighter stars are superimposed. Superimposed on this dense background are clusters of many ages. Ancient clusters, billions of years old, sit alongside intermediate age groups and young associations. Their coexistence illustrates the continuous star-forming history of the galaxy. Some clusters are compact and well-defined, their stars tightly bound. Others are more diffuse, spread across wide areas. Their distribution is not symmetric, with certain regions of the bar holding more clusters than others. This irregularity reflects the influence of gas flows feedback and the lopsided gravitational potential of the galaxy itself. Gas remains present in these regions, though in smaller amounts than in the outer disk. It collects into clouds along dust lanes where it is dense enough to form new stars. Observations show that even in the central bar, star formation continues. Small, H2 regions glow faintly surrounding clusters of massive young stars. These nebulae are less extensive than the Tarantula Nebula or the other giant complexes in the outer disk, but their presence shows that the central regions are not dormant. They continue to produce stars even amid the crowded environment of the bar. Dust lanes cut across the light of the core, their presence revealed by dark bands against the bright stellar background. These lanes absorb and scatter visible light-hiding stars behind them. In infrared views, they glow softly, showing that they are warmed by surrounding stars. The dust marks regions where gas is still available for star formation. It also shapes the visual impression of the core, breaking the uniform glow into segments. Some lanes follow the orientation of the bar while others curve across it, showing that the distribution of gas is influenced by both internal dynamics and external disturbances. Supernova remnants are scattered even here, though they are more difficult to detect against the bright background. Their shells appear as faint arcs expanding into the surrounding medium. The remnants enrich the gas with heavy elements, adding to the already high metallicities of the core. The young stars that form here inherit this enrichment, showing higher abundances than their counterparts in the outskirts. The cycle of birth and death is thus compressed into the central regions, where generations follow one another in rapid succession. Kinematics within the core are complex. The bar distorts the rotation, creating elongated orbits that differ from the circular motions of the outer disk. Stars move in streaming patterns and gas flows are channeled along certain directions. The velocity field is patchy, reflecting the combined influence of the bar, the asymmetry of the galaxy, and the repeated disturbances from interactions with companions. This irregularity is not chaotic, but structured with patterns that can be followed across the central regions. The flows reveal how the core is continually reshaped by both internal and external forces. Variable stars are abundant in the core. Cephids pulsate with regular brightness changes, tracing the youngest populations. Aurora Lyrae variables flicker more subtly, marking the oldest populations. Together they provide a detailed map of the stellar structure, showing that the core is not uniform but layered with populations of different ages. These variables serve as natural beacons, each one a signal of the epoch in which it formed. They are scattered across the bar, ensuring that no part of the core is devoid of their presence. Superbubbles and shells also appear even amid the dense stellar background. They are carved by clusters of massive stars whose winds and explosions push gas outward. In some cases, the bubbles remain closed, enclosing hot interiors. In others, they rupture, releasing gas into the surrounding medium. The scales are smaller than in the outer disk, but the principle is the same. Feedback reshapes the medium, clearing some regions and compressing others. The result is a landscape of cavities and arcs woven into the dense stellar field. The central regions are chemically enriched more so than any other part of the galaxy. This is visible in the spectra of young stars, which contain high abundances of heavy elements. These elements were forged in earlier generations and recycled into the gas that formed the current stars. The metallicity gradient that spans the disk reaches its peak here, with the core holding the richest populations. This enrichment gives the central regions their distinct chemical identity, separating them from the poorer outskirts. Compact remnants of massive stars such as neutron stars and pulsars are present in the core as well. Though not visible in ordinary light, they are detected through radio and X-ray observations. They are the endpoints of massive stars that once dominated these regions. Their presence adds another layer to the picture of the core, reminding the observer that stellar death is as common here as stellar birth. The density of stars ensures that both processes occur constantly interwoven into the fabric of the galaxy. As one continues inward, the field becomes so crowded that individual structures overlap. Clusters merge into the background shells, intersect with dust lanes, and variable stars are scattered throughout. The impression is not of isolated features, but of a continuous environment where every part is influenced by others. The core of the Large Magellanic Cloud is therefore a place where density feedback and enrichment reach their highest levels, producing a view that is complex, crowded, and layered with history. Deep within the central regions of the Large Magellanic Cloud, the environment becomes a tapestry woven from gas dust and stars of every age. The bar, already dense farther out here, merges into a hub where the highest concentrations of light and matter coexist. The background glow of red giants is so continuous that it appears almost uniform, yet closer examination reveals patterns, clusters, and variable stars embedded within it. This inner bar is not static. It is a place of constant activity where gas flows converge, star formation is sustained, and feedback from massive stars reshapes the medium at smaller scales. The crowding of stars and nebulae makes this region appear layered, with each line of sight intersecting multiple structures at once. One of the most striking aspects of the inner bar is the way gas collects along its length. Molecular clouds persist even here, despite the density of stars concentrated along dust lanes that weave through the stellar light. These clouds appear as dark streaks across the background, hiding stars behind them. Infrared views reveal their glow, warmed by the surrounding radiation field. They are the reservoirs from which new stars continue to form. Within some of these clouds, young stellar objects are detected still embedded in their birth material. These stars are invisible in optical wavelengths, but shine in longer wavelengths, showing that even the most crowded regions of the bar harbour active star formation. Clusters populate the inner bar in great numbers. Some are ancient, containing stars that have orbited together for more than 10 billion years. Their compact forms and metal-poor stars make them distinct against the enriched background. Others are intermediate-age clusters, stable groups that preserve the memory of star formation episodes billions of years ago. Still others are young associations, only a few tens of millions of years old, containing bright blue stars that illuminate their surroundings. This coexistence of clusters of all ages demonstrates that the inner bar has been a persistent site of star formation throughout the galaxy's history. Supernova remnants are scattered through the inner bar, though their detection is challenging against the brightness of the background. They appear as expanding arcs and shells, their edges glowing faintly where shock waves encounter gas. Each remnant enriches its environment, dispersing heavy elements into the interstellar medium. These elements are then incorporated into new stars forming in the surrounding clouds, ensuring that the cycle of enrichment continues. The presence of numerous remnants indicates that the inner bar has seen repeated episodes of massive star formation, followed by the deaths of those stars in explosions. Superbubbles exist here too, though their scales are smaller than in the outer disk. Clusters of massive stars excavate cavities tens of light years across, pushing gas outward into shells. Some of these shells overlap, producing irregular patterns where arcs cross one another. In places where the shells rupture, hot gas escapes into the surrounding medium, creating chimneys that channel energy away from the central regions. X-ray observations reveal the presence of million-degree plasma within these superbubbles, a phase of the interstellar medium that is invisible in ordinary light, but significant in shaping the balance of pressures. Variable stars fill the field, their regular pulsations adding subtle rhythms to the light of the inner bar. Cephides marking younger populations are scattered along the bar and into the arms. Their pulsations make them standard candles, and their distribution maps the depth and tilt of the galaxy. RR Lyrae variables marking ancient populations are also present, showing that the oldest stars are not confined to the halo, but penetrate the central regions. Together, these variables form a bridge between past and present, demonstrating that the bar has been both a nursery and a refuge for stars across the galaxy's lifetime. The kinematics of the inner bar are complex. Stars move in elongated orbits aligned with the bar's axis, their velocities deviating from the circular paths seen in the outer disk. Gas follows channels defined by the gravitational potential, flowing inward along some lanes and outward along others. The flows are irregular, disturbed by feedback, and by the asymmetric placement of the bar within the disk. Some regions show inflow as gas streams toward the center, while others show outflow where winds and explosions have pushed material outward. The coexistence of inflows and outflows creates a circulation that constantly reshapes the composition of the inner bar. Metallicity peaks here the highest levels in the galaxy. Young stars formed in these regions show abundances of heavy elements, far above those of the outskirts. This enrichment reflects the repeated cycles of star formation and death that have occurred in the bar. Each generation of massive stars has added to the pool of heavy elements, so that subsequent generations are progressively more enriched. The result is a chemical landscape that contrasts sharply with the metal-poor populations of the halo and outer disk. Dust remains pervasive, breaking the glow of the inner bar into patches and filaments. Some dust lanes are narrow, running like threads through the light. Others are broad, casting wide shadows. In infrared, the dust glows faintly heated by the stars that surround it. It plays a critical role in shielding gas from radiation, enabling star formation to proceed even in these crowded regions. The dust also gives the inner bar its distinctive appearance, dividing its brightness into mottled sections. As the view focuses on smaller scales, details emerge in the form of filaments of ionized gas compact star clusters and shells of supernova remnants. Each structure overlaps with others, producing a layered impression. The field is crowded not just with stars, but with the results of their interactions with the medium. Feedback has created an environment where the cycle of star birth and death is compressed into a small volume. Stars form, shine, and explode, and their products enrich the gas from which the next generation will emerge. The density ensures that these processes occur continuously, leaving little space untouched by their influence. The innermost regions of the Large Magellanic Cloud are thus filled with complexity. Every line of sight crosses dust clusters, remnants, variables, and shells. The mixture of populations, the high metallicity, and the crowded structures combine to create an environment distinct from the outer disk and halo. It is here that the galaxy's history is most clearly written in overlapping layers, each one a record of birth, evolution, and feedback. The bar, the gas, and the dense stellar background merge into a single continuous field that defines the visible heart of the galaxy. At the deepest point of the inward journey through the Large Magellanic Cloud, the exploration reaches the innermost regions where the bar, the clusters, the dust lanes, and the crowded field of stars overlap into a dense and luminous hub. The stellar density is so great that the background glows with a nearly continuous radiance, a haze of unresolved stars that provides a foundation for every other feature. Against this glow, bright clusters, supergiants, and variable stars stand out, but no region appears empty. The inner core is a place of superposition, where every line of sight intersects multiple populations and structures layered on top of one another. The overall impression is of a system where no single component dominates, but where all components blend together in a crowded balance. Ancient stars remain present even here. Red giants and RR Lyrae variables fill the background, marking the oldest layers of the galaxy. They sit alongside younger stars and clusters, ensuring that the core is not only bright, but also chemically and chronologically diverse. The presence of these old populations confirms that the center of the Large Magellanic Cloud has been occupied since the earliest epochs surviving through the long history of interactions and feedback that have shaped the system. Their faint but steady light blends into the background, giving the core its luminous base. On top of this base, young populations shine with far greater intensity. Compact clusters filled with blue stars mark recent episodes of star formation, each one a burst of activity within the central environment. Their light is concentrated and bright, contrasting with the diffuse background. Surrounding them are H2 regions, glowing volumes of ionized gas sculpted into arcs and filaments by the radiation of the massive stars within. Dust lanes weave around these regions, creating dark patches and silhouettes against the bright glow. These features demonstrate that star formation in the core continues even in the most crowded parts of the galaxy. Supernova remnants contribute further structure. Expanding shells of enriched material push outward, creating faint arcs that overlap with dust and gas clouds. Some remnants are compact and still bright, while others have grown large and faint, blending into the surrounding medium. Their presence indicates that massive stars have recently ended their lives here, injecting heavy elements and energy into the environment. These remnants ensure that the gas of the core is continuously stirred and enriched, feeding back into future generations of stars. Superbubbles exist even in these crowded regions, though their scale is limited by the density of surrounding matter. They appear as irregular cavities excavated by clusters of massive stars acting together. Their shells are fragmented and often intersect with dust lanes or other bubbles, producing a chaotic network of arcs. In some places, the shells have ruptured, venting hot gas into the surrounding medium. The interiors of these superbubbles contain plasma at temperatures of millions of degrees, revealed only in X-ray observations. Though hidden from the eye, this hot gas adds pressure and helps maintain the balance of phases in the interstellar medium. The kinematics of the core are complex, shaped by the offset bar and the irregular gravitational potential. Stars follow elongated orbits aligned with the bar, while gas streams along channels carved by both gravity and feedback. Some flows move inward, feeding the dense regions where new clusters are forming. Others move outward, pushed by winds and explosions. The result is a circulation of material with inflows and outflows interwoven across small scales. The velocity fields measured in these regions show gradients and distortions, evidence that the core is not in perfect equilibrium, but in constant motion. Dust plays a vital role here, absorbing light and reshaping the appearance of the core. Dense lanes of dust run across the bar, breaking the light into patches. In some places they align with gas flows, while in others they cut across them. Their uneven distribution creates mottled patterns, where some fields glow brightly while others are dimmed. In infrared maps, the dust glows faintly, warmed by the dense stellar background. It serves as both a marker of the gas reservoir and a regulator of star formation, shielding gas from radiation, so that collapse can occur even in the crowded environment. Variable stars are abundant in the core. Cepheids trace the young populations, their rhythmic pulsations standing out, even against the dense background. RR Lyrae variables scattered throughout trace the old populations. Their coexistence ensures that the core contains markers of both ancient and recent epochs. Observations of these variables allow astronomers to measure distances, structure, and composition across the central bar. In the view of the core, they are simply part of the dense crowd, their steady cycles adding subtle variation to the light. The metallicity of the central regions is the highest in the galaxy, reflecting repeated cycles of star formation and enrichment. Young stars here contain heavy elements far above those of the outskirts, evidence that the core has been enriched again and again by generations of massive stars. This high metallicity shapes the properties of the stars themselves, influencing their colors, lifetimes, and spectra. It also ensures that any future stars formed here will begin life already enriched, carrying forward the chemical legacy of the core. Everywhere in the inner core, the cycle of matter is visible. Gas flows inward along the bar, collects in dense clouds, forms stars, and is then dispersed by winds and explosions. The process repeats, layering new stars on top of old ones, enriching the medium further and driving the circulation of matter. The result is a dynamic equilibrium where creation and destruction balance each other to maintain the crowded complexity of the core. Each arc, cluster, and filament is part of this cycle, no feature existing in isolation. The innermost regions of the Large Magellanic Cloud therefore appear as a densely woven environment. The continuous background of old stars, the bright clusters of young populations, the variable stars of many ages, the shells of supernova, remnants, the cavities of superbubbles, the flows of gas, and the lanes of dust all combine into a single field. The view does not end with a sharp feature, but with a seamless blend of structures, each contributing to the identity of the galaxy's core. The exploration of the inward journey reaches its deepest point here, where the density, enrichment, and complexity of the Large Magellanic Cloud are at their greatest, and where every component of the galaxy is intertwined into one luminous hub.